this is Junichi Horikawa, and this is the 19th episode for VEX for Algorithmic Design. And the topic for this episode is about the basics of noise. And this is the topic that I'm going to talk about today, starting with explaining what noise is, and then starting from Perlin Noise, which is the most basic one, then go to Simplex Noise, and then do some exercises for Perlin Noise. Then I'm going to talk about the concept of periodic noise, how you can use it. Then explain about the flow noise, which is the combination of a Perlin noise plus a periodic noise. Then I'm gonna explain about the vector field related noise, which is called curl noise. Then I'm going to explain a cellular related noise such as Worley Noise, Alligator Noise, and Voronoi Noise, and how you can use them. Now let me first explain what noise is. When you say noise in computer graphics, it is often meant as gradient noise. It is mostly used for procedural textures in computer graphics in order to create a texture such as a cloud-like textures or a marble-like textures and so on, which is kind of a brother to a random values, but compared to the random values, you do have some control over the pattern you can create by selecting various noise-related algorithm together with several parameters. Same as random functions, a noise function needs you to set a seed value. And most of the cases, this seed value for the noise is location-based values, such as position or atp attribute in Houdini. And let's say you have a 2D grid like this and you want to use the center of each cell as the seed for the noise function. And here's the reason why the noise is called as gradient noise. That is because when the location for the seed used for the seed is close enough, then the value is also going to be close. The closer the distance is, the closer the value you get out of the noise function using the location. For example, if you got the result from the noise function like the value 0.1 at this location, then the neighboring value will be really close to this value, such as like 0.2, 0, 0.15 or something like this. And next to the neighboring to this one will be close to this values, so something like 0.3, 0.2, 0.0 or something like that. And same for the other cells. The cell which is close to this one, like this one, will be close to this value. As you can see that by having a far distance between the cells, if the location is far enough, then the value you will get out of the noise function will get the difference between the two values will be bigger. But when the distance between the two value is close, then you get a small differences. And that's the main principle for the noise function. And most of the noise function available in Houdini shares the same concept. The difference between the various noise function is that they use a different algorithm to generate each of the numbers. And I'm gonna briefly explain each of the noise function, what types of values will produce and how you can use them. But just by understanding the concept how the noise function works, how the distance and the value is related, then you can use any kind of noise function pretty easily and for many purposes, with a lot of flexibility since you now have a understanding how the noise function works. For example, you'll easily be able to create a wavy surface or ocean-like surface pretty easily using noise functions. Now I'm going to start by explaining the Perlin noise and how we can use it, which is one of the most basic noise function, which was founded by a Ken Perlin in 1985. And by understanding how you can use this Perlin noise, you'll be able to use other types of noise pretty easily. Now the basic Perlin noise accepts three types of parameters. One is in 1D, one is in 2D, or one is in 3D. As an output, you can output either a float value or a vector value, and each of the value for x, y, and z for the vectors will be in the range between 0 to 1, and also for the float, which is in 0 to 1 as well. And just like the random value, you can use each of the location as a C value, and you can output a different value for each location. And the difference between the randomness is that the closer the distance is between the points, then you get the closer value, either float or vector. Now we're not going to go deep in how the Perlin Noise algorithm works. You can, if you are curious how this algorithm works, you can go to the Wikipedia for the Perlin Noise and see how it's being defined. Basically, it can create a smooth wave-like pattern, and I'm just gonna show you how you can use it and how we could use it for many purposes. Now let's go to Houdini and start by creating using a Perlin Noise. I'm gonna create a geometry node and then start with a really simple setup. I'm going to create a grid, then show the wire shaded. Let's also set the resolution of this grid to 50 by 50 by setting the rows and columns high res enough. Now the name of the function that I'm going to use now is called noise, and which is the most basic noise function you can use in Houdini, which is a Perlin noise based function. So let's try to use this. And if you look at the parameter set, you can use either float or vector value or vector 4 as an input. And as an output, you can either output float value or vector value. In computer graphics, float value is mostly used for gradients, and vector value is often used for the directional value. Now let's see how we can use this. I am going to create a point wrangle to control each of the point on a grid. Connect with the grid, and let's name this noise basics. And first I'm going to get the result of the noise value by using a noise function and the point position of each point on a grid as a parameter, since this is a vector value. Now, the result of the value should be in between 0 to 1. Now what I'm going to do is to use this value to change the y value of each point of this grid and see what happens. And this is the result you get out of a noise function and using as a height value. And you can see that the height is gradually changing based on the point position. Compared to the randomness, it has a smooth connection between the neighboring point in terms of the height. And that's the kind of a main benefit of the noise function. Based on the location, you can smoothly create a gradient based values. Now currently the size of the mountain and the position of the mountain is kind of a fixed, and you cannot do anything with it with this setup. But by changing the location of the main point that you have inputted as a parameter, and also changing the distance between each point, you can control the size of the mountain or the location of the mountain as well. So let me show you how you can do that. First of all, as I said, by changing the distance between the neighboring point, you'll be able to change the value differences between the points as well. And you can easily check that out by changing the resolution of this grid parameter. And if you change these on row, you can see that the values next to the grid have more differences compared to when the value was in 50. You have less differences in terms of height, but if it's like 7, you have more differences in terms of height for the neighbor points. Now, you can procedurally control the distance by not changing the original geometry itself, by just multiplying the input right here. I'm using the @p attribute, which is the point location, but multiplying this by some scalar value, you'll be able to easily scale down or scale up this location value. And by doing it, you'll be able to control the size of this wavy mountain. Let's see how we can do that. Okay, so I'm gonna go create another point wrangle and connect with the grid. Let's name this noise scale. And what I'm gonna do is simple. First of all, I'm going to create a variable called val and then use the noise function just like we did last time and change the y value for the each point with this value. And what I'm gonna add now is the multiplication to this point position. Let's name this scale and promote the slider so that you can control this value. Let's also change the range of this slider value, the float slider value between 0 to say 5. Okay. Now currently the scale value is equal to 0, so as a result, by multiplying with the location, all the point will be converted into 0, 0, 0 location. Now by slowly raising this value up, you can see that you have more big wave, big mountain wave starting to appear. And compared to with the value when the scale was equal to 1, which is the original location of the noise value, you can see if the scale is smaller, then the height difference between the neighbor points is much smaller than before. And making this scale smaller and smaller, you have less and less differences between the neighbors. And that is making this big mountain wave. But instead, by increasing the value, instead you have more differences in between the neighboring points, and you see more jittered mountain like this. So by just changing the multiplication for the location inside this noise parameter, you'll be able to control the size of this wavy mountain. And this is one of the essential techniques you need to remember when you're going to use noise function. Now you can also control either x direction or y direction or z direction as well by multiplying at p with a vector value. Let's say if you want to only control the x direction smoothness or scaleness, then you can say scale, and for the y and z you can say 1. Now by doing it, by changing this parameter, you are only changing the smoothness or the size in x scale. And by raising this up, only the x scale, x directional distance is changing. If you multiply this, then the difference, the distance between these two values or 2 points in x direction is going far. And as a result, you get a lot of differences between the points in x neighboring. And if you make it lower, you have more smoothness in x direction, so on. So by understanding how this multiplication works, you can control the directional value in terms of how the noise scaling works, which could also be based on UVs or any other parameters. Now let me make this back to a single scale value so that x, y, z will be affected by this single value. The next essential technique that I want to show you is how you can shift or move the mountain, the whole mountain location to other position. Currently, by changing the scale value, you can change the size of the mountain, but you cannot change the location of the mountain itself. Now, in order to do that, it's pretty simple. You just need to think that this is a location-based seed. So what you just need to do is to add a additional put location value as an offset. Now let's try to do that. I am going to copy this noise basic and let's name this noise shift. Then I am going to create a vector value called as offset. Then let's just change the x value for now. So I'm going to create a parameter called shift for the x value, and for the y and z value I'm gonna set 0. Now what I'm gonna do next is to add this offset value to this noise value parameter. So adding a current p position with an offset value. Now this is the shift value, and let's try to change the range between 0 to 10. If I change the shift parameter, you can see that the whole noise is moving in x direction, and that's how the shift works. Currently I'm adding the x value to the current point position. As a result, all the noise value seems like it's shifting to x direction. So if you move this x value to y value for the shift as a parameter, then you can shift it to y direction, since y direction is upward on, so it looks like it's creating like a water-like wave. And if you move to the z direction, then now it goes to a z direction. So one of the technique I use often is if you want to use a 2D grid with the noise value, something like for the purpose to create a wavy-like surface, I'm often set a shift value to the y direction to create a animated wave. So you can see that by changing the y, since the 2D grid doesn't have a y direction, there's no every location in y is equal to 0 in this grid. So by shifting these y value for the whole geometry, it just changing the whole wavy looks. Okay. So by setting some time-based parameters like $t for the shift, you can create like water-like animation pretty easily. Now what I have just explained is the essential stuff when you use a noise function, any kind of noise function, which works for most of the noise function, even if the algorithm is different. And by understanding this essential, I'm going to show you several examples or exercises how you can use them for different practices. But before doing that, I would also like to show a Houdini noise function called X Noise, which is based on the noise algorithm called Simplex Noise, which was developed by the same person called Perlin, kind of a updated version of Perlin Noise, which is said to create a better result than the Perlin Noise. So let's see how we can use that as well. But mostly the way it can be used is same as the noise function that I have just introduced. You can check the set of parameters and output you can use with this X Noise function, which is for the Simplex Noise algorithm. And pretty much it's the same with the noise function that I've just introduced. And if you look at the description here, the Simplex Noise is very close to Perlin Noise, except with a sample of simplex mesh rather than a grid, and this result less a grid artifacts. So meaning this noise function can create a more smoother result than the noise function. So if you found out that the noise function is creating some glitches, then using X Noise might help you. But most of the cases, using either one is just fine, I think. Doesn't give you much differences in most of the cases, in my opinion, or in my experience. Now I'm going to copy the grid. Then I'm going to copy one of the code that I write here. So I'm gonna copy this noise scale. Let's name this X Noise. So what you need to do is, instead of using noise, I'm just going to rename this to X Noise. And that's pretty much it. It just do like what it did in noise function. So using either noise function or X noise function is okay, I think, when you want to use this algorithm. Since it had said that the Simplex Noise is a better version of Perlin Noise, maybe using X noise instead of noise is better in most of the cases, I guess. Though I myself use noise function a lot rather than X noise, I tend to forget this X noise existence. But since now you know that this one is a bit better, maybe you can use this instead as a default noise function. Now let's try to do several noise related exercises how we can use noise for algorithmic design. Let's start by creating animated surface together with a box being copied to each of the point on a surface, and then use a noise value for the scaling value as well for those boxes on the surface. Well, I am going to create another grid. Let's set the rows and columns to really high, like maybe 100 to 100. Maybe 50 to 50 is fine. Okay, and then I am going to create a point wrangle and do pretty much the same things as I did previously. I'm going to name this noise wave surface. And first of all, I'm going to create the noise value by creating a float variable called val, and use the noise function with a point position on a grid. Then I'm going to multiply this with a parameter called scale, and then also add with a shift value, which I'm only going to change the y value. So I'm going to create a shift parameter for the y value, and for the x and z I'm going to set it to 0. Okay, and then I'm going to promote those parameters, 2 parameters, one for the scale, one for the shift. Now after I have created this value, I am going to change the height of each of the point by setting the y value using the value that I have just created. Now this value is in between 0 to 1, so in order to control the height, the maximum height, I'm going to multiply this by some additional parameter called height. Okay, now if I raise this height up, you can control the maximum height of the noise value, and then I can change the shift as well as the scale. Now let's set the range for each of the value. I'm going to go to the edit parameter interface, and for the height I'm going to say it's from 0 to 5. And for the scale and shift I'm going to keep it as it is. Okay, so by raising up the height value, you'll be able to have more differences on each of the mountain. Okay, now I can play with all the parameters that I have created. Now what I want to do next is to create a animation for this surface. So just like I did previously, I'm going to set some time related parameter for the shift value with this one, which is used for the y value adding to the point based position. Now it could be either at $T or $F. I'm going to use T for this one. Now if I play it, we'll create an animation. Let's also toggle this real-time toggle. And if you want to make it faster, you can multiply this T by some value more than 1 to make it faster. Now let's also color the surface based on the height or the noise value. So I'm going to create an additional parameter for this each of the point other than the height value. So I'm going to create a parameter like a noise val. I'm going to store this value that I have created to this noise value attribute as a float. Now let's create a color node and connect it with this surface and change the color type to ramp from attribute and use the attribute that I've just set, which is named as noise val. Now you can set some colors you want to set in between 0 to 1. Currently it's set from black to white. I will give you some gradient from black to white for the surface based on its noise value. Now maybe I can set the left one to something like blue and the right value to be something like red. And let's make this arrange like these. Okay, so the lower part looks blue and upper part looks red now. Okay. Now next thing I would like to do, I would like to set a p-scale as well to each of the point and use it for controlling the size of the box which is going to be copied to each of the point. Now what I'm going to do, going back to this point wrangle, I am going to create another parameter called p-scale and use the value itself as well. Now if I look at the geometry spreadsheet, what's the values distribution is, which is either noise value or p-scale, you can see that the range is indeed in between 0 to 1, but there's not the value, there's no value which is really close to the 0 or close to 1. It's mostly the value is in between, like looks like in between 0.25 to 0.75. And this range also makes it different with the random value. Random value will evenly create a value in between 0 to 1. But when you use noise related function, you get a value in between something above 0, like 0.2 or 0.3, to something like 0.7 or 0.8. And it is explained here when on the noise VEX function page. The noise is in the range between 0 to 1 with a median of 0.5. The distribution of the noise depends on the dimension, with higher depending dimensions approaching a Gaussian distribution of noise values. So if you want to expect the value 0 or value 1 when you use a noise value, then you actually need to remap the value that you have created out of a noise function. So let's say the minimum coming from this noise function might going to be 0.3 and the maximum is going to be like 0.7. Then what you need to do is to first clamp this value by 0.3 and 0.7. So the value which is smaller than 0.3 will become 0.3 and the value bigger than 0.7 will become 0.7. Now after doing that, you can use a fit, which is the remap function. And currently, since I have used the clamp, the minimum was always going to be 0.3 and the maximum is going to be always 0.7. 0.7. And then change the new range to 0 to 1 so that you have more chance to get the value in between, the real value in between 0 to 1. You have more chance getting the value in 0 or 1 in this case. So I have used this clamp and fit function for the p-scale so that you have a possibility that you get a 0 value for the p-scale or 1 value for the p-scale. And let's check that out. Going into the geometry spreadsheet, and for the p-scale, at some point you have 1, the maximum 1 value, and you also have like 0.9, 3, 2, 1, and 0 as well. So that's one of the technique you can use. Okay, now that we have set a p-scale value to each of the point, I am going to create a box. Not this one, box, and use a copy to point stop node to copy the box to each of the point. Now let's also scale down the base box size to something like 0.25. Okay, so the lower the noise value is, the p scale goes close to 0, so the you cannot see the box anymore. The upper the noise value goes, then the value goes close to 1, then you'll be able to have original size of the box being shown on each of the point. And if you play this, you'll be able to see the animated box on the animated surface. You can also change how the noise being distributed by changing the scale, changing the height, or changing the speed. Like this. Okay, so this is one of the simplest example you can use noise to create. Now let's try to do another exercise. Previously I was using a location of the grid as the parameter for the noise function. Now what I'm going to do next is to use the 1D scalar value for the parameter for the noise as a practice. So let's see how we can do that. So first thing I would like to do is to create the line facing upward. Let's also set the length to 5 and set the number of points to 50, so that you have a bunch of points you can modify. Now what I'm gonna do now is to create a spiral curve out of this line by changing each of the point location, and each of the point location has its point number starting from 0 to 49 if you have total of 50 points. And I'm going to use this point number as the parameter for the noise function and use it to control the thickness of the final pipe geometry created out of this curve. First of all, let's try to create a spiral curve out of this straight line, like using a trigonometry, the basics of trigonometry. So I'm gonna name this spiral thickness noise spiral thickness. Now first thing, I am going to create a angle variable which I'm gonna use to control the location of each point based on the trigonometry. So to do that, I'm first going to retrieve the point number, then multiply this by some step angle value. Now I'm going to use a radians, and inside the radians I'm going to create a parameter to control the step angle. And let's set the range of the step angle between 0 to 90. So if I set this to 30s, and the first point will have an angle 0, the second point will have an angle 30, and the third point will have an angle 30 by 2, so 60 degrees. And convert it into radians like this. Okay, now I also would like to create a parameter for the radius of the spiral curve. So let's set it as a float value. Like this. Let's set it to some value. Now it's time to change to each of the point position. If you remember, you can change the you can set the point location in circular by using cosine and sine. And in this case, by changing the x and z coordinate by using cosine and sine, you'll be able to change the xz plane coordinate as circularly. So for the x, I'm going to use cosine, and for the y, I'm going to keep the original y position out of this original point position, then use sine for the z. And for the cosine and sine, I need to use the same angle, so I'm going to apply ang to cosine and ang to sine. Now also, if you want to change the radius, you can multiply the radius to the cosine and do the same for the sine for the circle. Now, as a result, you'll be able to create a spiral curve like this, and by changing the step angle, you can change how much it's been twisted, and you can also change the radius as well. Now let's set a p-scale attribute to each of the point for the spiral curve so that I can use this p-scale attribute to change the thickness of the pipe that I'm going to create later. So I'm going to create a noise value. I'm going to call this attribute, the variable val, and use noise function. And I'm going to use a ptnum itself to use it for the C value, which is the scalar value. And also I am going to multiply this by some scale related value to change the range of this, the size of this ptnum. Okay, and what I'm going to do now is to apply a p-scale attribute directly with this value that I've just created using noise. Now let's promote the scale value. I'm going to start with the 1. Now, if I look into the geometry spreadsheet, the p-scale, let's say everything is 0.5, so there seems to be no differences. So let's try to change the scale to something lower. Let's see what happens, and you can see there seem to have much more differences start to happen. Okay, so let's try to use this p-scale to change the thickness of the pipe, which is going to be created to this curve. Okay, so I am going to use a poly wire in this case, and use the division like 12 to make it smooth. And then for the wire radius, I'm going to use the expression to read the p-scale at each point using point expression function, and looking at the self node by saying // plus op input dot 0. So this is going to be the path for the node, the current node. And then for the second parameter, I am going to use $pt, which means equivalent to @ptnum in VEX. Then I'm going to use a p-scale attribute at 0 position. Now, so this is kind of a result, what you get out of this value. Now it seems like there are a big difference between the neighboring point numbers in terms of the size. So by changing this scale, you can smoothen out the differences based on the point number. Or if you want to make more differences, you can raise these scale up. At the end, it will become just 0.5. Okay. Well, maybe something like 0.15 is good. Overall, the thickness looks a bit too thick. So let's try to multiply additional parameter called thickness to use it as a maximum thickness value, since value is in between 0 to 1. And by changing this thickness value, you can control the base thickness value like this. Okay. And probably you might also want to clamp the minimum and maximum since the range of this p-scale is currently in between 0.1 to 0.2, which looks a bit of small ranges in it. There's not much range for this. That is because I have used this thickness. So maybe it's better to check by having another attribute like val to directly store this noise value and see its range. Now the value range is in between 0.7 to 0.28. So maybe we can do another clamping that we did previously for the P scale. So what I'm going to do is first clamp this value by 0.25 to 0.75 as a minimum maximum. Then I'm going to use a fit to remap this value, which should be in between 0.25 and 0.75 now, to 0.0 to 1.0. Now that you have more thinner and more thicker thickness available for the pipe. Okay. Now what I'm going to do next is to create an animation so this thickness will move upward or downward based on the PT number. So what we could do is to create a shift value that we did for the wave surface as well. For the wave surface, we have created the shift value for the Y direction, but for this one, the input for the noise value is scalar, so we can add an additional scalar value for the shifting. So I'm going to name this shift as a new parameter. And I'm going to use some time-based value like $t. Now, if you play, so you can see that the thickness is changing by going downward. You see that the thinner one is going downward, creating animation like this. Additionally, if you want to color this, you can add additional color node, probably in between this, and then use the ramp from attribute and use val, and then change this with some color gradient you want to use. The noise value can also be used to output vector values. So in next exercise, I'm going to show you how you can use the vector value as an output value. Specifically, I'm going to change the color of the surface by using a noise function, since the color can be expressed using vector, X, Y, Z, or RGB. So first, I'm going to create a grid. And then let's change the rows and columns to 50 by 50. And what I'm going to do is to apply the color to each of the point using point wrangle with a noise function. Okay, now I'm going to name this noise color. Now, it's going to be pretty similar to what we did in order to output the float value. In order to output the vector value, you just need to create a vector variable instead of float variable in order to create a vector noise value. So, if you want to create a color value as a vector value, first you create a vector variable like this, and then use a noise with, for example, using P as a seed value. Then we can update the current CD attribute for each point with this color to set the color of each point on the surface. And you can see that the color is smoothly changing based on the point position. And you can also multiply this point by some scalar value, like making a scale parameter. And making this smaller, you'll be able to have more smoother changes. By making it bigger, you have more randomness starting to appear. Okay, you can see that the color is a bit too blurry, too light, and that is because it's pretty related to the the range of the noise value that has been created by using this noise value. If you look at the range of this, each of the RGB, it's in between 0.22 to 0.75. So same as the float output, it will create XYZ as a vector value, but each of the XYZ coordinate will be in the range between somewhere around 0.25 to 0.75. So let's try to clamp this color value as well in order to make the contrast of the color a bit higher. Okay, so what I'm going to do, the process that I'm going to use is pretty much the same. The clamp can also be used for the vectors, and the fit can also be used for the vectors as well. So what I'm going to do is pretty much the same as we did before. You first set the minimum and maximum to clamp the value, so that the value less than 0.25 will be clamped to 0.25, value more than 0.75 will be clamped to 0.75. And then use the fit, which the minimum is 0.25 and the maximum 0.75, and remap this into 0 to 1.0. As a result, the contrast of the color becomes a bit higher. And this still should work on any surface other than grid if you try to use a sphere instead. Let's make this as polygon. Connect it right here. Let's also raise up the frequency so that you have enough points to color this up. Maybe a little bit more, maybe 220. Okay. And let's also make this scale a bit bigger. I'm going to change the range of the scale from 0 to 5. Okay, looking good. Now what I want to do now is to animate this color changing. And to do that, what I was doing previously is to create a shift value for either X, Y, or Z coordinate. But the problem right here that we have right now, that all the X, Y, and Z coordinate is used for each of the point in this case if we are using a sphere. So if we just try to change the Y value as a shifting to animate the Y value, then you probably have the animated color value but going from top to bottom or bottom to top, which is going to be a bit too artificial for the animation. So let's see what I mean. First of all, I'm going to make this outside as a variable. Let's name this pos, and multiplying the current position by scale, and have this position applied inside the noise as a parameter. Then what I'm going to do now, after creating the position, I'm going to change, or I'm going to add the shift value to only the y coordinate of this position. So creating a CHF shift. Okay. Now by moving this one, you can see that the color change is happening vertically in Y direction. If I use $T, the color is moving from top to bottom like this. So there is some direction you can see out of this change. In some of the cases this is fine, but if you want to have all the colors to change gradually without any directional information, then what you need is an additional axis to use it for the shifting. Now going back to the documentation page for the noise function, you can actually check that you can use the vector4 as an input as well and output a vector value. So currently we were using XYZ as a position seed, which is this one, but we can add additional axis as an input for the noise. And for the additional one, the fourth parameter, for the fourth coordinate, we can use the shift to animate the noise value addition to the point position in 3D. So let's try to do that. I am going to create a vector 4 value after I have created the point position based value, which is the vector 3. So I'm going to create like a variable called v, which is a vector 4 value, and create a vector 4 value. First 3 will come from the position, so position pos.x, pos.y, pos.z for the xyz value, and for the fourth value I'm going to use this shift value. Okay, and remove this one. And then I am going to use this v value that I've just created as a parameter input for the color noise. By doing it, if you play it, you can see that all the color start to change without the directional information now. That is because I'm using the fourth parameter, and all the x, y, z is kept as it is. So there is no position change is happening, you're just changing the value for the fourth value. Which is also another essential technique you want to remember when you are dealing with a 3D geometry and together with some additional shifting value, probably for animation. Now, as a last exercise for the Perlin noise, I'm gonna show you a bit more interesting way to use noise to create an interesting surface. Specifically, I'm going to create a ripple-like effect on top of a surface using noise function. Now, the base surface could be anything, so let's try using like torus. And let's have enough points so that we can change the point coordinate in high detail. So let's give the rows 100 and the columns 200. Okay, that looks good. Now, first thing I would like to do is to create a scalar noise value out of using each of the point position as a parameter for the noise function. And just to mention, all the things that I'm doing here can be replaced using X noise as well. So using either function is fine, noise or X noise. Now, let's create a point wrangle. Since I'm going to use the point position as a seed for the noise parameter, and also I will also like to create an animation. So just like I did for this coloring, I'm going to create a vector 4 as a parameter. Okay, so starting by creating a vector 3D, which is coming from the position. So current position multiplied by a scale value to control the smoothness of the noise. Okay. Then also create a vector 4 value for the final parameter value. Let's call this v, and set position x, position y, position z, and for the final one I'm going to create a shift, just like we did for the coloring. Now I am going to create a float value as an variable, then use noise to create a scalar noise value using v as a parameter. Now we can quickly check the distribution, how this value is being applied for each of the point by using this as a color value. So I'm going to update the color using this value. Okay, so it is now being shown as black and white. Maybe I might want to have more mountains by scaling this up. So let's set the range for the scale to 0 to 5. Okay, now I see more pattern. Now what I want to do here is to, out of these values, I want to create a ripple-like pattern by extruding or moving the point coordinate up and down like a ripple wave. Now to do that, one idea is to change or use this value as a angle for the trigonometry. Okay, meaning I can use a sine function, and inside this sine as an angle I can use this noise value and use this result as a value to move this point to the normal direction. Okay, so let's try that out. So first of all, we need to convert this value into something can be useful for the angle. And currently the range of this value is in between 0 to 1. So we need to convert this or remap this into a angle friendly value. So if we want to, let's say if we want to use a sine function, then for the one wave it's in between 0 to 2 pi. Okay, so if you just want one single wave using this as an angle, then you need to multiply this value by pi multiplied by 2.0. Then this value will become in the range between 0 to 2 pi. Then we can use this as a angle for the sine, and we can update the value itself with the new sine value. Now the sine value will have a negative value as well, so everything which is negative become really black if you try to use it for the colors. Now let's comment this out, and let's use this value to move the point coordinate to the normal direction. So the normal coordinate can be retrieved by accessing to @n. So modify the current point position by adding the normal direction, multiply by the value. We'll be able to control the point coordinate. Now it seems like the size of the movement is a bit too big, so we need to control this by multiplying some values to this final value here. Let's name this wave height. So I guess it should be less than 1, somewhere right here. And you can see that the point is starting to deform based on this sine value, which was using this noise as a angle. Now since it is just one single wave, it's a bit hard to see what's going on here. It just looks like a random wave pattern. So by adding a more wave numbers to this angle, might be able to see more differences, or might be able to see more ripple-like effect. To add more ripple numbers or wave numbers, what you just need to do is to add or multiply some numbers, it could be integer numbers, to this one to control the number of waves you can use. So 2.0 multiplied by pi is equal to 1 wave. So if you multiply by 2, you have 2 wave numbers. So let's have a parameter as an integer called wave num. And by increasing the wave number, you start to have a lot of wave happening, start to happen. Now currently the normal of the first surface is a bit weird, so we can fix that by creating a normal node after this. And maybe the wave height is a bit too strong, so let's reduce this one. Let's also see what happens here. Now you start to see more ripple-like effect on a surface like this. Now maybe we want to have more resolutions on this torus, so let's give like 500 to columns and 250 to rows. Now we start to see more clearly what's happening here. Okay, that looks good. Now let's try to increase the range for the wave num, something like 0 to 30. And if I raise this number up, you can see more waves is happening. More ripple waves is starting to grow. Now more you have, more glitches you get, so maybe keeping it smaller, like 15 or 10 might be good. Okay, and by moving this shift you can change how the ripple being changing based on the noise, and this noise value is used for the angle value for the sine wave, and the sine wave is creating this kind of ripple effect. So by combining several simple equations, you'll be able to create such a really interesting pattern on a surface. Now let's try to use a time-based value for the shifting and see how it's being animated, like at $t. Alright, looks really interesting. And changing the scale, you can change the scale of the ripple pattern. Making the scale bigger, you have more smaller ripples. Small scale value will create a bigger ripple pattern. Now these were the exercises for Perlin Noise, and this exercise can also be applied for many other various noise functions, so please try to remember what we've done here. Everything we've done here is pretty essential. Now the next noise that I would like to introduce is a periodic noise, which in fact is the same Perlin Noise based noise. But the difference between the noise that we've been using and this periodic noise is that by using the periodic noise, you can create a tiling-like pattern, a seamless pattern which can be connected like a tiles to create an infinite scale of the noise value. And if you look closely, you can see a same pattern repeatedly being created. And this periodic noise is available for Perlin Noise, but also for many other various noises. I'm not going to go into all the other periodic noise patterns, but I'm going to explain how you can use this periodic noise for the Perlin Noise. Then you'll have an understanding how you can use it for other types of noise as well. Now, for example, if you have a grid like this and the size of 1 by 1, and first thing you need to specify in order to use the periodic noise is to set the size for the x, y, and z coordinate for the repetition, for the tiling steps or tiling size. Now it has to be in an integer, so if you want to use all these grid as one tiling pattern, then if this is x coordinate and this is y coordinate, then in order to use a periodic noise, you have to set the px to 1 and py to 1. And in addition to this, you also need the location information as a seed to use as a noise value, the Perlin noise value. So same as for that kind of parameter, it's the same as the one that we have been doing using. So each of the location of the grid cells matters to change the value. So say if you have a 0.1, 0.2, or 0.1, 0.3, something like that. By having the information px equal to 1 and py equal to 1, and by extending the input geometry, currently the tiling that you have is equal to 1 to 1, but if you have input the tiling or the grid size like 2 by 1, like this, the value you get here is the one you get the same with the one that you get here in the 1 by 1 tile. So all the values that has been created like these is being copied right here, and all the others as well. And the value next to this one, which is right here, is going to be a smooth value, a gradient value, which is the difference is small in terms of this distance. So this is how this periodic noise works. It will create the seamless tiling pattern, tiling noise values based on the size that you have set for X, Y, or Z for a 3 dimension, which could be useful for many purposes. So I'm gonna explain how we can use it and what will be the good practice to use it for. Let's first look at the documentation page for the function that we're going to use, which is called as pnoise, which is to use a Perlin based algorithm to create a periodic noise. And addition to the parameter that we've been using, which was a position based information like X or vector value or vector 4 value, you need to add additional px, py, pz, or pt as an integer value, which is going to be the size of the periodic tile size in x, y, z, or w direction, or in this case called as t, meaning maybe a time-based value, I guess. Now let's see how we can use it on Houdini. Let's start by creating a grid. And I'm going to set the rows and columns to 50 by 50. Then I am going to create a point wrangle so that we can create a noise value for each point. I'm going to call this pnoise tiling. Okay, and first of all, I'm going to create a value for the tiling size, which is going to be a integer size. Okay, so I'm going to name it as rep or tile size. Okay, let's start with 1. Now I am going to create a float value variable and call a pnoise function. And let's use the @p as a noise seed value, and since this is a vector 3 value, and we need to set x, y, z tiling size value. So I'm going to copy this one 3 times to set the tile size for the x, y, and z. Okay. Now I'm going to use this value to change the height of each point by setting the y value, y coordinate for the point, with this value multiplied by some height as a maximum value. Okay, and raise this up. Maybe I need more range. Let's say 0 to 10. Oops. Okay, and if I raise this up, you obviously see some repetition happening on a x direction for 10 times, I think. And also, if you look closely to the z direction, there is also some small wave happening to the z direction, and it's happening 10 times as well, and z direction. And why it's 10 times is because the size of this grid is equal to 10. So if I change this to 5 by 5, then the repetition becomes 5 by 5. That is because I am setting the tile size as 1. Okay, so let's make this back to 10 by 10. And if I change this tile size to 2, then the tile size become 2 by 2 by 2. So if we are using 10 by 10 grid, then in total you have 5 by 5 tile. So this is one tile and this is another tile, and you can see a clear repetitions between this one and this one and this one, and it's repeating for 5 times in X direction and also 5 times in Z direction. And if you change this to 5, now you have 2 by 2 tile pattern. One is this one, and one is this one, and one is this one is this one, and it's repeating smoothly. So this is how this periodic noise works. And let's also check this seamless connection by setting the color as well. So I'm going to create another attribute called call with this value, and let's use this value attribute to change the color using ramp from attribute, reading the color attribute, and then let me check, and let's change this color range, let's say from red to blue. So that you might be able to see more clearly the repetition pattern. Maybe I want to have some black as well, and white on the right edge. So you can see there's some similar pattern right here and right here, right here and right here. So 2 times on X direction and 2 times on Z direction. Same for these black patterns and so on. Now, as an advanced exercise using this periodic noise, let's try to create a 3-dimensionally tiled pattern, which you can repetitively expand in X, Y, and Z direction as a geometrical pattern, a 3-dimensional geometrical pattern. And to do that, I'm going to try to use a volume in this case. So first of all, I'm going to create a box as a base geometry, and let's set the size to 2. Okay, now I'm going to create a volume node to convert this box into a volume. And let's set the resolutions of this volume to something like 50, and also name this density value as density as a scalar value. It's fine. I'm going to use a volume wrangle, and this is where I'm going to use a periodic noise to create a single tiling geometry, tileable geometry, or repeatable geometry. Okay, and let's name this P noise 3D tile. Now let's first create an integer value to determine the tile size. I'm going to name this TL, TS, CHI tile size. Okay. Now let's set the tile size to, say, starting from 1. Now since the box size of this one is equal to 2, and I always want this box to have a 2 by 2 tiling for some reason. So in order to do that, we need to multiply this TS by the point position to use it for the random seed. I mean the noise parameter as a seed. So I'm going to create a position value which comes from at P and multiply by TS. Okay, so if TS is equal to 1, then you just keep the same size as the current point, which is you'll be able to have a 2x2 tile. If the TS becomes 2, then you need to have a total 4x4x4 box in order to have a 2x2x2 tile. So to do that, you need to multiply this 2 value with P so that the minimum and maximum will be in between -2 to 2. In other words, the bounding box size is 4x4x4. So that's kind of reason why I did this here. Now let's create a noise value. I'm going to make it as a float value, and I'm gonna directly use it for the density later. So P noise and position, and we have a three vector values, so I'm going to use TS for 3 times X, Y, and Z. You can also change the value for Y or Z or X if you want to change the number of tilings on X, Y, or Z direction, but for now I'm going to use this all the same. Now I am going to set the density for each of the voxel by applying this value itself. Now let's also promote the tile size so that you can see that it's controlling the size of the tiling. Let's keep it something like 2. Now what I want to do out of this volume is to retrieve the polygonal surface out of this volume. So there are several ways you can do it. One way is to use like a volume surface node or convert node. What I'm going to use is one node called convert volume. Okay, which will convert this surface or volume into a surface using this ISO value. So I'm gonna set the ISO value somewhere close to 0.5 since the median of the volume is 0.5. Now you can already see that this is already a tiled geometry, which is in 2x2x2 tile. So by increasing the density of the volume and also increasing the tiling number right here, you can create as much number of tiling as much possible, like this. But what I want to show you is to trim out the single tile out of this geometry, then use it to repeatedly copy in X, Y, Z direction for your purposes. Because setting the high value for the density, it might not be a good idea because it costs you so many CPU process. Okay, so what I'm gonna do next is to use a Boolean node, and together with the box which has the size equal to 1 by 1 by 1, and use the operation something like intersection between the surface and the solid with the intersect. And as a result, you'll be able to get this intersected surface like this. And this is actually a repeatable surface for the top part or left part on the front part. So let's try to check that out. Okay, so to do that, next thing I'm going to do is to create a grid which has the size of 1 on X direction, Y direction, and Z direction. Now I'm gonna quickly create that using a attribute wrangle. Attribute wrangle, and let's change this to detail to run once. I'm going to create a 3 nested loops to create a number of points on each coordinate X, Y, and Z. Now this is for the X. Now for the second nested one, this is for the Y. I'm going to change this to N, N, N. And for the third nested one, it's going to be used for the Z axis. I'm gonna change this to T, T, and T. And then create a point using IN and T as an XYZ coordinate. Set IN T. Alright. And promote those XYZ slider. And you'll be able to create a grid, 3D grid, which has the size 1 by 1 by 1 for each cells. Alright, now what I'm going to do, I'm going to name this 3D grid, is to use copy to points to copy this single tiling geometry to each of the point and see if the geometry connects smoothly. And if I do that, you can see that it sure is connecting the geometry smoothly without any glitches. It looks great. Now let's keep this size a little bit smaller and let's try to change some parameters that I have set here, like the tile size. Still keeps you, the more tile size you have more complex geometry for a single tile. Less you have more simple tile like this. And probably it will be interesting if we could animate this geometry as well, using some shift related value like we did for the noise exercises. Now to do that, we could, instead using a vector 3, we could use a vector 4 value by adding a shift value to the fourth coordinate. Okay, so I'm going to first create a shift parameter. Let's call that float shift. Okay, and then I am going to create a vector 4 value after we have created this vector 3 value by combining this position for X, Y, and Z. And then the fourth value, I'm going to use shift. Then instead of using this position as a seed value for the noise, I'm going to use this V that I've just created. And let's promote this shift value and change this to a time-based value. Okay, it's a bit hard to see the changes. Now let's see if I have done correctly. Okay, well, since we have used the V value or the vector 4 value, we need to add one more tiling pattern or tiling size pattern. And since this fourth value, the shift value is a different metric. The XYZ is a position based one, so using TS makes sense to use the same value, but for the fourth one it's on the different metrics. It's a time based value, so we could change this to some different value. If we change this to 1, then the range of the repetition for this time is in between 0 to 1, meaning if we could create a value for if we could create a time-based value when the frame is it and the first frame, make this shift value 0, and if it's at the 240, then make the shift as 1, then we can smoothly repeat the animation as well by using this periodic noise. So let's try to do that by setting this shift value, which is this one, to value related to this frame value and is always in the 0 to 1 range. So you can do that by, first of all, have this current frame value and divide it by a frame end, which is this 240. And as a result, you'll be able to get a value in between 0 to 1. And this in result will create a smooth animation from end to first. Now let's check that out. Now it's a bit too slow, so let's reduce some sizes or for this one. And also I'm going to reduce the size of the single volume, let's say 30. And maybe the time is a bit too slow, so I'm gonna set to 60. And you can see it's changing the value from 0 to 1. It changes a shape up just a small bit. Maybe the tile size or the repetition size for the fourth coordinate might equal to 1 is a bit too small. Maybe we could increase that as well. But you can see that it's smoothly connecting the animation from end to first. Okay, so let's go back and let's have another parameter like int tt, which is going to be the time-based size, time size starting from 1, and I'm going to use this tt or time size to first to this shift value, okay, and also right here for the repetition number, which in result, if tt is equal to 2, then you have a range between 0 to 2, and the maximum range or tile size will be equal to 2. Okay, so if I raise this up something like 4, you have more drastic changes based on time. By increasing more, you have more changes. Makes the speed of the change faster. If it makes this smaller, then you have small changes, but still keeps you the repetitive or you have a smooth connection between end to first, because it is it has the same concept. It is still a periodic noise. See? Works pretty well. Now that I have just explained the periodic noise, the next thing I would like to introduce you is the mixture of the noise and the periodic noise, which is the function called flow noise, which is this function called flow noise. Now this is the flow noise that we're going to use, and the difference between the noise that we've been using is that this is basically a non-periodic noise. The only difference is that you have a second parameter which is called flow, and this is the only parameter which is a periodic, which is between 0 to 1, and you cannot control the size of this periods. It's fixed to 0 to 1. So you can consider that this is kind of a small variety of P noise, a periodic noise. You can actually by using periodic noise, you can actually set the period, the size of the tiles to non-periodic as well. By if you go back to the P noise function, and for the px, py, pz, it says integers, and if you set the px, py, pz to 0, then which will create this direction as non-periodic. If you have more than one, then you have you're going to set the periods or repetitions. But if you set these values to 0, then it means it will give you a non-periodic values for this specific coordinate. So you can consider the flow noise as this kind of, if you are using a vector 3 inputs together with a float value for the flow parameter, then it's pretty much the same as this one, being px, py, pz equal to 0 and pt equal to 1. If you go back here, that's similar to this value here. So just by understanding this parameter differences, the result you get is pretty much the same between the periodic noise and this flow noise. And this is pretty useful when you quickly want to create a noise pattern non-periodic noise pattern, but based on the time, it goes back to the original, or goes back to the first frame's noise pattern by just using the second parameter as a repeating value. So most of the case, what I use this for is to use this second value for the time-based value, so that you have a repeated animation, repeatable animation, or GIF-like animation. So let me show you one example using this flow noise to visualize something. Well, this time I'm try to create some vector field using this flow noise, animated vector field, so that it can repeatedly animate it, even if goes from end frame to the first frame, smoothly connects to the first frame. Okay, so I'm going to first create a cube, or a cube, and then I am going to create a volume node. Let's set the sampling divisions to 50, and also I'm going to set the rank to vector, so it will be a vector volume. I'm gonna name this to velocity. Any name is fine. I would like to scatter points to this inside this volume, so I'm going to set the initial value to 1. And I am going to scatter some points inside this volume. Okay, and I'm gonna use this to visualize the volume trail later. Now I am going to create another volume wrangle connected to this volume. Let's name this flow noise trail or vector field. Now the usage of the flow noise is pretty much the same as the noise function. You just have additional parameter for the periodic value. So first of all, I'm going to create I would like to use the point position as the seed for the noise. So I'm going to create a point position based on the current point position. And let's have some multiplication to control the scale of the point position. Okay. And let's also set the range from 0 to 5. Alright, now next I would like to create a shift parameter which is going to be animated. So shift, F, shift. Okay, and I'm gonna use it as a float value. Now I am going to create a vector value named as direction with a flow noise function. And for the first parameter, I'm going to use position, and for the second parameter, I'm going to use this scalar shift value, float shift value. And as a result, you'll be able to retrieve a vector value which the x, y, and z coordinate is in between 0 to 1. So it will give you some positive directional vectors at this point. Now let's try to visualize this first. I'm going to update the velocity value with this direction. Okay, now I am going to change the shift and see if things are changing. Maybe I would need to change some scales. Okay, so something is happening here. Right, now what I would like to do is to change visualize the vectors on the volume using volume trail. And connect the point to the first input and volume to the second input. And now you can see the visualized vectors. I still see the volume as well. Okay. Now looks like these. And by changing the shift from 0 to 1, you should be able to change its animation. But since the second parameter is the periodic value and it's in between 0 to 1 range, so by changing this shift based on the timeline or frame based value, by changing this to 0 to 1, then you'll be able to create a repeatable animation. So to do that, you can divide the current frame with end frame like we did last time. And if we play it, it should smoothly connect from end frame to the first frame. Now currently, since all the XYZ coordinate is positive, so it's going to a similar direction, which is a bit boring. So let's try to make this a bit more omnidirectional. And to do that, one of the way you can think of is that the range of this flow noise is in between 0 to 1, and the medium is 0.5 for all x, y, and z. So, meaning if you subtract this by 0.5 for each coordinate, then the range of this flow noise, the result of this equations will be in between somewhere around minus 0.25 or minus 0.5 to positive 0.5 maximum. Okay, for all x, y, z coordinate, and as a result you'll be able to see more omnidirectional flow pattern like this. Now it becomes more interesting, and by changing the scale you'll be able to see a scaling differences or have some turbulence like flow pattern. Now if I play this, you see there's no glitch between the frame end and the frame start. It smoothly connects from end to frame. That is because I'm using this flow noise for the shift which is in between 0 to 1 as a periodic size. Okay, you can do the same things with the P noise as well by setting the shift, the fourth coordinate to 1 and all the other coordinate to all the x, y, z to tiling size to 0, which will create the same effect like this one. But if you just want to make the last parameter or last coordinate to be periodic, then using flow noise might make more sense, which is more easier to use. Now the next noise function that I would like to introduce you is the curl noise function, which is also based on the Perlin noise, but it only gives you a vector value as a result. And it is often used to create a vector field related values. And it's going to be much easier to create vector field like compared to the one that I have just tried using flow noise. So let's try to create another vector field using this curl noise function. Now I am going to copy this set that I've created for flow noise. Okay, so I have this box and have this volume, set the sampling divisions to 50 and have it set as vector, have velocity, and created a scatter of points inside the volume. And also for this one, this is the one that I'm going to change using curl noise, so I'm going to name this curl noise. And let's also remove all the parameters that I've created here. Let's clear this code up. Okay, now let's start using curl noise to create a similar flow based value or noise. First of all, I am going to create a position value as always. So based on the position of each voxel, multiplied by a scaling value. Okay, let's start from 1. And then I'm going to, I would like to animate this as well, so I'm going to create it as a vector 4 value as a final input. Okay, and use position X, position Y, position Z for the XYZ value, and for the last one I'm gonna name it as shift to control the fourth coordinate. Now I will update this velocity. Now I need to create a directional vector. using curl noise. Okay, using this value that I've created right here. Okay, now I am going to update this velocity using curl noise. Oops. Using this direction that I've just created. Okay, now let's also create, let's also promote the shift value that I have here. Let's have T as an input, and for the scale I'm going to set some range between 0 to 5 so that I can control the size of this flow vector value. Now if you joined it, visualize this one, it gives you more cleaner, more smooth flow vector field compared to the one that I've created right here. You see that there, the smoothness of this flow is not that smooth enough compared to the one that I have right here. Okay, so it gives you more clean vector field and which is because created from the two cross product of a to Perlin Noise, which makes it really smooth like this. And if I play it, you can have a smooth animation like these. Now this one is not, this curl noise is not periodic, so you have some ending. The connection between the end frame and the first frame is not connecting smoothly. But other than that, it gives you more clean flow value compared to the flow noise or normal noise value. If you want to create a repeatable flow animation, then I would suggest using periodic noise. But if you want to, if you don't care about the smooth connection between the frames from end frame to first frame, then using this method, using this curl noise, makes more sense to create a vector field, create more turbulence like field like these. Looks really good. All right. Yep. And you can control the speed by multiplying like t by some other values to slow down or make it faster as well. The next noise function that I would like to introduce is one of the cellular based noise function, and which is called Worley Noise. And when it says Worley Noise in Houdini, there is 3 types of Worley Noise available in Houdini as a function. One is using a Euclidean distance, one is using Manhattan distance, and one is use Chebyshev distance in terms of inner algorithm. Each of the distance method using a different method to calculate the distance between 2 points. Now in most of the cases when we imagine the distance between 2 points, we are using this Euclidean distance. And I'm gonna explain this Worley noise based on this Euclidean distance. Now the way Worley noise works is that first of all you give a bunch of points position as an input, as a sample. Then as a result it will create a various seed points on a space randomly, like something like these. And then what you get as an output is 4 value or 2 or 4 value, which is called in between f1 to f4, which is the distance between each of the point on which you're going to use as an input and the closest seed from that point, closest distance to the closest point. In this case, the closest distance between the picked points on the grid and the seed point is this one, and this is going to be f1, and the second closest is going to be this one, f2, and third distance is f3, and fourth distance is f4. And by adding all these values together, you can actually create or ocean-like landscape for each of the point if you use it as a height value at each of the point, which is pretty interesting. And if you subtract f2 by f1, if you do a subtraction f2 minus f1, then it will create some boundary between the seed points, like a Voronoi pattern, something like this, which you can retrieve this boundary position at 0 y value equal to 0, and the other points having some value more than 0. So if the point is on this border, you get value 0 with this calculations. By using this characteristic, you can also create more like a cell-like pattern as well, using this noise, Worley Noise. Now, as I said, in terms of Worley Noise, you can choose 3 types of distance measuring metrics. Now, the one that I'm explaining here is called Euclidean, which is calculating the distance, the direct distance between the points to points, okay, straight. But if you choose something like Manhattan distance, what you get is the distance by adding the z coordinate or y coordinate and x coordinate, and adding this distance together with this distance. So the distance will become x plus y in this case. If it's in 3D, then you have another coordinate as well at z. So this is the Manhattan distance. So it's the distance, when you calculate the distance using the Manhattan distance, the distance became longer than the Euclidean distance. And there's another distance metrics called Chebyshev distance, which if you want to calculate the distance between these points, then the distance will be a distance between this line and this line right here. So this is going to be the distance for the Chebyshev distance. If you're calculating the distances between these points, then the distance will be this distance. And that's the Chebyshev distance. So based on those different distance metrics, what you get as a result in terms of f1, f2, f3, and f4 is going to be different. And as a result, by adding all these numbers, you'll get different kind of pattern, same as this one. And let's see how it looks like by checking it out in Houdini and see what can it be used for. First, I'm going to create a grid. Let's make it really high res to have enough sampling points to use it for Worley Noise. Okay. And then I am going to first test out the f2 minus f1 using a simple parameter set for the Worley Noise. So I'm going to use the point wrangle, and I'm going to name this W noise cell. Now let's check what kind of parameters we could use. And if we look at it, first of all, when it says position, it is basically the same things as what we were using for the seed for the noise. It's going to be the position value to calculate the noise value. So it's going to be the main thing. Could be float, or 2 floats, or vector 2D, or vector 3, or vector 4. So any dimension is okay in this case. And when we have this and a characters before the name of the input, it means this is the output parameter, which is you can just input empty variable to these inputs parameters, and by calling this function, those parameters or those variables will be updated with this function. So you have either seed f1 and f2, or seed f1, f2, f3, f4, just like what I have explained. And you can also make this noise periodic by adding some period x, period y, or period xyz, or period xyzw as a additional parameter to make it as a periodic noise for this Worley noise. So it's this single W noise, which is using a Euclidean distance for the Worley noise, is pretty flexible in terms of creating many kinds of many types of noise values using the Worley noise algorithms. It could also, it's good to know that you could create a periodic noise out of this same function as well. Okay, I'm gonna try with the really simple parameter set first. Let's try out this one. Since what I want to try out is the F2 minus F1 to see the border of the cell, and maybe we could also use this seed as well. If we look at what this seed is, it is a number of seed points which indicates the uniqueness of the cell. So maybe we could use this seed value to change the color of the cell or something like that. Okay, so let's try to use this parameter set, and as an output, this is the void function. It doesn't output anything, so we can just use it as it is. And what we need to do is to prepare these output parameters as a variable. Okay, now by understanding what parameter set is, let's first create a output parameter variable. First of all, integer seed and float f1 and f2. Now let's call a W noise, and for the position value I'm going to use P for the point location. Maybe I can also multiply with some scale value to change the size of the P. Okay, and also for the second parameter I can set this output parameter seed and f1 and f2 for the third and fourth parameter. Now as a result, all the values seed, f1 and f2 should be updated. So let's try to see how it's been, what kind of value we get. Okay, so if we just try to use f1 in this case, now we don't see anything. That is because I haven't set the scale yet. So let's make this larger, and it looks like we have some kind of Voronoi-like divisions. That is because it is actually a Voronoi pattern, because we are just using the first closest point distance to show up the height. Now if we just use 2, it becomes a bit more complex, and we cannot really see what the characteristics of this one out of it directly. Now if we subtract f2 by f1, just like I explained, now you see some border, start to see some border on the y equal to 0 positions, which indicates the border of the cell, and these one are the cell itself, and each one is having a different seed value in this case, which is outputted from this one. And if we see how it looks like, we can create it as a float value and put it as, store this seed value to this attribute. Maybe let's set it as integer, and you'll see this really high number either on negative or positive, and this is the unique number for each of the cell, indicates the unique number for each cell. Okay, so what I want to try out next is to use this seed value to change the color for each cells. Now currently the value is too big in order to use it for the random seed. So what I'm going to do is to change the attribute to float and multiply this by some small decimal numbers, something like this, and make these values small enough. Okay, like this. Probably this is good enough. Now I have set the seed for each of the point, and if the cell is the same, it should share the same seed value, like this. Now, I can use the color node to color each of the point based on this seed value. So I'm going to use random from attribute and use seed. Okay. And as a result, you can see that each of the cell, which is divided by this border, is being colored differently, like this. Okay, so I think you can kind of use this Worley Noise analytically like this as well. And if I change this height back to F1, looks like this. And you can see, you can also clearly see that it's changing its color based on its cell. Right? I'm gonna make this back to F2 minus F1. Now this is to show the characteristic how this Worley Noise works. Now let's try to use this to create some interesting shape, like an ocean surface, animated ocean surface. And let's also make it like a periodic in terms of animation as well. Now I'm going to create another point wrangle, connect it to the grid. Let's name this W noise surface. Now going back to the parameter set, and what I would like to use now is a position plus a shift value for the animation. So maybe using vector 4 might make sense, and I want to make it periodic as well for the last shift value, and all the others, all the position could be non-periodic, so I can set the period related value to 0. Only the last one could be set to some higher, more than one value, okay, to make it periodic. So probably I could use the last parameter set, and I would like to also test this F3, F1, F2, F3, and F4 value as well. By adding all these values, you'll be able to get a really complex surface shape out of this Worley Noise. So let's try to see what happens. Okay, so let's remember that we're going to use this one. Now we need a 5 parameter set. One is seed and the other 4 is F1 to F4. So int seed, and then float F1, F2, F3, and F4. Okay, now let's create a position value out of a current position multiplied by some scale value that we've been doing a lot today. Okay, let's start by 1. Now I'm going to create a vector 4 value having these position as x, y, z value. And then for the last one, I'm going to use create a shift value. So let's name this shift somewhere else, like float shift, chf shift. And probably I could have a time size or time step size as well, for the periodic size as well as an integer. So let's say time size is equals chi time size. Okay, and I'm going to multiply this to this shift right here and have this shift being applied to the force coordinate for the vector 4. Okay, now everything is ready. I think we can call this W noise. First input is going to be this vector 4 value, and the second value is the seed, and F comes F1, F2, F3, F4. Now we also need to set the periodic noise, periodic size for X, Y, Z, and W. Now for the X, Y, Z, I want to make it non-periodic, so you can set 0 for X, Y, and Z. And for the last one, I can set this T size, which I have set right here. Okay, which also indicates the speed of the animation as well. Alright, now as a result we'll be able to get these F1 to F4, so I'm going to add all these values together. I'm gonna name it as, say, W val is F1 plus F2 plus F3 plus F4, and I'm going to apply this value to an attribute called col to change the color later. Now I am also going to update the height of the point using this value. So W val, and probably I would like to control the height as well using some parameters. I'm going to create another parameter called height as a slider. Now everything is ready. I'm going to click this one to promote all the sliders and see what would happen by changing these values. Okay, so first of all, the scale changes the scale of the pattern straightforward, just like other noise value, and the height is changing the height of this noise value, and changing the shift value, you can change its animation, or you can change its variation by changing the W coordinate. And the time size will change the speed of the change. If you have higher value, the change from 0 to 1 is drastic. If it's 1, it's really slow. Okay, and since this is the periodic noise, if you go from 0 to 1 and go back to 0, it will smoothly connect. So I can make this animation based or frame based by dividing the current frame by the frame end, which will create a value in between 0 to 1 based on the frame value. And as a result, by creating animation, a plain animation, it smoothly connects from end to first. And I can increase the speed by changing the time size. Okay, so it already looks like an ocean surface now. So let's try to make it a bit more like an ocean by changing the color based on the noise value. So I'm going to change this to ramp from attribute, and I am going to use the attribute that I've created named as col, which should change the color, but we need to check what's the range of this color value by adding all F1 to F4. So let's go back and see the geometry spreadsheet for the color. And let's go up and see the minimum is around 0.5 and the maximum is about 3.5. So let's say for the color range, the color attribute is in between 0.5 to 3.5. Alright, now it looks more like the ocean surface. Now let's make it blue, light blue on the middle, and as a result, it really looks like an ocean. Now if we play it, we'll create a repeatable ocean-like surface. And if you want to make it bigger and if you want to make it repeatable, you can create this surface repeatable by setting the repeat size or tiling size right here instead of 0, which is pretty useful, I think. Okay, which creates really interesting surface like you see here. Alright, now if you remove one of the values like F4, it will create more simple surface like these. If you delete this one, create more simple one. And if you have just F1, it becomes more like a Voronoi surface. By adding all these together, you have more detail for this cellular noise value, which gives you a really interesting surface. Okay, so that's how the Worley noise can be used or work. Now let's also check other types of Worley noise using different distance metrics, like the Manhattan distance and the Chebyshev distance. So but the parameter set is pretty much the same for all the other Worley noise based noise function. So what I'm going to do is to copy this part together with this grid right here, like this, and then I'm going to name this first of all, I'm going to test the Manhattan noise, so I'm going to name this MW noise surface. Okay, so what you need to do is just rename this W noise to MW noise, and that's just it. In order to use the Manhattan noise, you just add M. As a result, you get something like this, more like a landscape or mountain landscape, a bit artificial, low poly, but looks like a mountain landscape. So let's try to color this out in different colors. Set. Now, first of all, I would like to check the maximum and the minimum for this color value. It looks like it's in between 2.5 to 6, around 6. So let's set this value to 2.5 to 6. And then let's change the color set, color gradient, starting from maybe green, and then change this one to something more yellowish, more something like these, and make it more like a dark red and became white to make it look like a snow. All right, and let's see this being animated. Yeah, well, it's a bit artificial in terms of the angle, but looks interesting. It does look somehow like a landscape. All right, interesting. Now let's also try another distance metrics, which is called Chebyshev metrics. Okay, so I'm gonna copy this again. This time I'm going to rename this to CW noise surface. And as you can imagine, what you just need to do is to rename this M to C. That's it. Okay, now it looks like these, and let's also check the minimum and maximum of the call value. So that is from 1.099 to 2.7. So let's say it's in between 1 to 3. So 1 to 3, and let's change the color again. I don't know what kind of pattern it's going to create, so looks more like mechanical chip-like a pattern. So let's make it like blue on the left side and red on the right side. Make something like ambiguous pattern. Looks like low res GAN generated image, if you know what you mean, if you know what I mean, from a deep learning. Okay, well, still interesting, could be useful for something. I haven't used this for myself, but could be useful for something, maybe using some mechanical like network or something like that. Now the next noise function that I would like to introduce you is the one called alligator noise, which generates a similar pattern compared to a Worley noise, but with different parameter set, which is pretty useful if you want to create such an ocean-like surface like we did last time with the Worley Noise. Now this noise function doesn't give you much of the analytical information like the Worley Noise did, like the border information or the seed information. But if you just want to create an ocean-like surface like you did with the Worley Noise by adding all F1 to F4, maybe using alligator noise is much easier. So let's see how we can use this. Now if you look at the parameter set, you can first of all you need to have a position, which is same for other noise function, and the simplest one is without any parameter other than the positions. Now if you want to control more, you have a value like turbulence, rough, or attenuous, I guess. And for the other parameters, you can also use this period X, period Y, period Z to make it a periodic noise as well, and just like the Worley Noise. So I would like to try out this value, or maybe this value, or probably I'll use this one to use it for the height for the ocean wave, making it a periodic noise so that I can copy paste on a grid to make it really large surface afterwards by creating just one tile. And let's also see what kind of difference you get by changing these three parameters: turbulence, rough, and at 10. I'm going to copy the grid from the Worley Noise. Okay, and I am going to create a point wrangle. Let's name this a noise. Okay, and then I am going to, first of all, create a position value at P multiply by scale like we did last time. Okay, now I am going to, since this is on the grid, so I kind of don't need to use it as a vector 4, but maybe I can just change the Y value as the shift value in this case. If you're using a surface like sphere, then using vector 4 to change the shift value for the animation might make more sense. But if you're working on with the 2D, which in this case on XZ plane, then the Y coordinate is not used. So in that case, I can use the Y coordinate as a shift value. So I'm just going to use this as a shift value like I did for the other grid. Okay, now for this one, I'm going to set FF divided by F end. Okay, now since I am going to use the time or the periodic for both the scale, both position and for the time scale, I'm going to create two parameter to control the size for the tiling for the position and size for the time. Okay, so, and both have to be integers. So first of all, I'm going to say pause size or p size chi pause size and t size chi time size. Okay, now let's start by 1 for now. Okay, now I'm going to set the grid size to 1. Okay, so that I can make this as a single tile geometry or single tile face. Okay, now what I'm going to do, I'm going to maybe bring this up after creating this p size and t size, and I'm going to, for the position, I'm going to multiply this with a p size, and I'm going to multiply this y value, which is going to be used as a time shift, with the t size. This. Okay, now it's time to create a alligator noise value using a noise, and first parameter I'm going to use a p size, or I mean the position. And for the second parameter, second, third, and fourth, it's going to be the periodic size for x, y, and z. So the x, z will going to use p size, and for the y, I'm going to use t size. So p size, t size, p size. Okay, now comes the specific parameter for this alligator noise. One is turbulence, one is roughness, and one is attenuation. Okay, so let's create that. And turbulence is in integers, so let's name this turb, chi, turb. And for the roughness value, it's going to be float, so chf, rough. Flow the attenuation, it's also a float, so chf, attenuation. Okay, now we can say turb, rough, attenuation. Now let's promote all the parameters that I have set. Okay, so for the position size, keep this to 1 for now. Okay, for the roughness, set it to something like this, and continues to 0.5 and turb width 1 for now. Okay, now what I'm going to do is to use this value that I've retrieved for the height of this plane. So add p.y is equal to val, and maybe multiply by some height value for the maximum, to set the maximum height. Okay. And if I increase this one, you should be able to change the height of this plane like this. And it should give you the repeatable tile set on the side, on the front side. And if you played it, it should give you a periodic time animation. Now the tile is a bit too big, so let's make this, maybe I should make this scale bigger in terms of range. Let's set it to 0, 10 as a range, like this. Okay, now I see a tons of repetition now. Now maybe I shouldn't add this, multiply this scale after all, in order to make it repeatable, I guess. So let's not have this one, but instead use this position scale to scale up. Okay, looks good. I'm gonna remove the scale value here, and the height seems a bit too high, so let's make it smaller. And maybe in order to make it like a ocean wave, maybe we need to look at this part. So let's make it negative right here. Now start to create something, looks like wavy surface, but it's not yet close. So let's see what we can do with the parameters we have here, attenuation, turb, and height. If we increase the turbulence, it looks like you can add some details, small details on top of the previous one. So it seems like this is an iterative value to add the turbulence value. Okay, looks good. Let's keep this 3, and the attenuous, it seems like you can change the extrusion height. So let's keep this something like 0.5, and for the roughness you can change how rough the pattern is going to be. So which is, might want to keep it as something like 0.4. Now I can also make this size a little bit bigger like this, and also set the height smaller. Okay, now it looks more like an ocean, starting to look like ocean surface. Okay, now I'm going to create an attribute called call and apply this value as it is, store this value from the A noise, alligator noise. Now let's go to a geometry spreadsheet and check the color value for the maximum and minimum, and it is around 0 to 0.7. So, but this 0.7, I guess it's coming from is this one, isn't it? If you make this 1, then you have from 0 to 0.5. Okay. Okay, it does look like it's affected by this attenuous. It seems like the maximum could be 0.7 or 0.8. So let's just create a color node which is in between 0 to 1 to use the color attribute, call attribute, to change the color set to make it look like an ocean. So starting with the white, and then use light blue, darker blue, more darker blue, and then finally black. Okay, now let's bring this up. Okay, now if I animate this one, looks more rough, and if I increase the time size, it will give you more random animation, but still repeatable. Alright, it looks good. Now changing the roughness, you can see a bunch of things happening. Maybe you can relate this to a wind, the strength of the wind, tenuous, the depths, the turbulence. I guess it's also related to the wind, if you want to relate this as a sea, ocean surface. Okay, now that looks good. Now what I would like to try out is to check if this is repeatable in position as well, in terms of X and Z. So what I'm going to do is to create a grid which each point should have a distance equal to 1 to 1. So to do that, I'm going to create a point like 4 by 4, and the number of rows 4 by 4, probably 5 by 5. Okay, which should create a size equal to 1 for each edges or each point distance. Now I'm going to delete the primitive and keep the point. Now let's try copying the base ocean surface to its points and see if it's repeating. It looks like it does. It cleanly makes a repeatable surface, and it is animating as like this. Okay, that looks satisfying. Alright, it's a bit slow since I have too many points for each grid. Maybe I should reduce this. Now the last noise type that I would like to introduce you is another cellular noise, which is called Voronoi Noise, which you can retrieve a similar value compared to a Worley Noise. But in addition to the Worley Noise, you can retrieve the center of the cell as a point position, and you can also set a parameter to change the jitterness or randomness of the seed position. So that's kind of a difference between the Worley Noise and the Voronoi Noise. And the Voronoi Noise, you can retrieve F1 and F2, which is the same concept as the Worley Noise, but you cannot retrieve F3 or F4. So it's a bit hard to create an ocean-like surface with this Voronoi surface, but instead you can have a bit more analytical information in terms of Voronoi using Voronoi algorithm. So the value that you're going to retrieve out of this Voronoi noise is pretty much the same as the Worley noise. I'm not going to explain the basic algorithm for this one. Instead, I'm just going to show you how you can use it in Houdini as a parameter set or as a function, and use some of the Voronoi noise specific values for some purpose. Now let's start by creating a simple Voronoi pattern using this Voronoi noise. Okay, so I'm going to start by creating a grid again. And let's set the resolutions to something like 200 by 200. Okay, now I am going to create a point wrangle. Let's call this B noise basics. And the Voronoi noise is called as V noise as a function for VEX, and here are the set for the parameters. Here are the parameter set for the V noise. And going through, you can see that there's another position which we were using the whole time. The new parameter introduced here is this jitter, which controls the randomness on X, Y, and Z coordinate, or in X, Y, Z, W coordinate. And as an output, similar to a Worley noise, you can get the seed value, or F1 and F2. And as an addition, you can get the position 1 and position 2, which is the seed point position for F1 and F2, for position 1, position 2. Now you can also make it periodic as well by setting an integer value. So the new parameters introduced here is this jitter and this point position for the seed, the center of the cell. Okay, so let's see how we can use these. So first of all, we need to create a output variable for the output parameter. One is the seed, just like we did in the Worley noise, and F1 and F2, and also the vector position 1 and position 2, which is for the seed point position. I'm also going to create a variable for the jitter, which is going to be used as the randomness. Okay, so I'm going to create it as a, and you can control the jitter for X, Y, and Z separately. So I'm going to create 3 parameters, or maybe I can use CHV and call jitter. Okay, so that I have X, Y, Z value separately being able to control. Now, let's try to use this Voronoi noise. Since this is the void function, there's no output out of this Voronoi noise. So we will just do just like the Worley noise. So first of all, I'm going to set a point location, maybe multiply by the scale as well to control the size. And then comes the jitter. And then seed F1, F2, and position 1, position 2 as an output parameter. And that's it. Okay. Now, what I would like to do is to see if we have any value retrieved, and by changing the height value for the point using F1, just like we did for the Worley noise. And it does what seems like a similar things to a Worley noise, but as you can see, this is currently looks really artificial, looks more like a square grid. Now you can change this by you can make this random by changing this jitter value. If you set the x value to 1, so makes only the x coordinate random. So you can see that on x direction, the position of the seed point, which is the center of each of the cell, become random. If you make the z value as 1 as well, then for the z direction it becomes random as well. Now we don't have a y direction for this one, so setting this one to 1 doesn't really shouldn't make any change. I did, yeah, I kind of did. Maybe it also changes the height position for the point, which also changes its pattern. So it does make sense. And the range for x, y, and z is in between 0 to 1 for these jitters. When I have tested, it only work in between 0 to 1. So that's the range. If you make it 1, then that's the maximum randomness you get. Just like we did for the Worley Noise, if you subtract f2 by f1, you get the similar cell division, and you get the border on the 0 position on the y direction, like this. Now we could also create a seed value, seed attribute from this seed multiplied by some small decimal numbers, and use this to color the cell. Random from attribute. Let's use seed to change the color like this. Now let's also try to use the one for the seed position, either position 1 or position 2. Let's try to use this position 1 and see how it looks like. Now what I'm going to try is to add the point at this position 1, which creates a bunch of points on the space, and these points are actually the center points of each of the cell. Now it's a bit hard to see which one is which, so I'm going to apply an attribute to this point, the same seed that I have right here. So set point attrib 0 seed pt with the f seed. Okay, now we'll give you a bunch of same colors for each of those points. I'm also going to set some groups so that I can separate those points later. So set point group 0, I'm gonna name this maybe seed by 1. Now what I would like to try is use a delete node to only choose the seed point and delete non-selected for the points, so that you'll be able to get a bunch of points like this. Now what I want to try is to use a Voronoi node that we have in Houdini and use this to create a Voronoi fracture, and if we get the similar Voronoi divisions like this one. Okay, so let's see that. I'm going to create another grid which have the same size but have rows and columns 2 by 2. Okay, and I'm going to connect this grid to the first input to the Voronoi fractures, and for the second input I'm going to use this center point of the seed at the point location for the seed. Okay, now it gives you this kind of Voronoi pattern. Now I would also like the color with the same color that I have right here. Okay, what's this one? So I think I can do that by transferring a copy cell points attributes. So to piece primitive, I'm going to copy this color. Oops, maybe not. Instead, I'm going to copy the seed value Okay. Now, let's color each of the primitive using a random from attribute and same seed value. Okay, maybe that was wrong. Okay, the reason why we get things like this is because we have so many duplicated points on the same location. So I'm going to use the fuse to merge all the position, all the points which is in the same location. Now we have like 177 points. Okay, and the color looks like this. Now I would like to compare this one with the one that I have generated right here and see if there's changes, and looks like it's identical. You see? So it just proved that this Voronoi noise will create a same Voronoi pattern by using the seed points that I have got here together with this Voronoi fractures. Okay, so this is kind of an analytical purpose that I have just done here. Could be used for an analytical purpose. It's pretty neat that you can create a center of points as well as this Worley based noise value at the same time. Now that we understand how this Voronoi noise works, I'm going to finish with some final exercise using this Voronoi to create a partition, the Voronoi partition on a volume using this volume noise. And it could also work with the Worley noise as well. Okay, so let's try to do that. First, I'm going to create a box. Okay, and then let's set the two volume to the let's create two volumes out of this box. Okay, one is called as seed, which will store all the seed values at each voxels. So I'm gonna name this seed. I'm gonna create another volume, and this one I'm going to call this density, which have all the values calculated by the Voronoi value, Voronoi noise. Now I am going to merge these together, and as a result you'll see two volumes being merged together like this. Now you can use volume wrangle to access both of the volume at the same time in single volume wrangle, which is pretty useful. So I'm going to use a V noise for the volume. Now in terms of the parameters, so there's a lot of things to do, so I'm going to copy the one that I've written here, somewhere around here. Okay, copy this one and paste it to this Voronoi volume wrangle. Okay, and let's promote this one and set the jitter to 1 by 1 by 1 for now, and also set some scale. Maybe set the scale range to from 0 to 3 for now. Now what I would like to do now is to update the seed value first from the volume with the one that I have right here. So I'm going to use seed. Now by doing it, you'll be able to fill in the seed volume with the unique seed information, which has a range between some negative really big numbers to positive really big numbers. Okay, for the volume density, it doesn't have to be in between 0 to 1, but could be in any range, but it's a bit hard to see the range. But if you want to check it out, what's the maximum, what's the minimum for the volume, you can go to a geometry spreadsheet, to the primitive, and go to the intrinsic, and then you'll be able to check the volume related value, like check this volume max value and volume min value to see what's the minimum for the seed and what's the maximum for this seed by looking at these intrinsic primitive attribute. And there are some other volume related values. I'm not gonna go into that one, but it's good to know that you know what's the range for the minimum and maximum for the seed. Okay, now what I would like to do now is to use this seed information to create a partition in between the cells and use it as create a wall as a partition. Okay, so let's try to do that using another volume wrangle. Okay, like this, and let's name this partition wall. Now what I mean by partition is that if this is the Voronoi cell, then what I would like to do is to visualize this border as a 3D surface. Okay, and the rule here is that the voxels, each voxel in this location has a unique different values. So if the seed value for this one might be like something -3, and the seed value for this one might be minus or +4, and this one could be seed equal to like 10 and so on. So in order to determine the border, what you can do is to see the differences between the neighboring seed. So at this voxel positions, the neighbor in this direction should have a different seed value compared to this one. So by creating a condition, checking the neighboring one, and if it's different, and only if it's different, then filling that space with a density will be able to create this kind of wall-like volume. And later on we can convert it into surface as well. So that's what I would like to try to do here. Okay, it sounds a bit more advanced, but we can actually do this with the information that we've been learning. Okay, so to do that, first of all, I am going to set the density setting, starting to set the density by 0 as a default. Now let's only look at the x direction and see the neighboring value for the seed. Okay, so to look for the next neighboring value and next neighboring and x direction in terms of the volume, you can use a function called volume index. And first value is 0, which is the number of input, and the second one is the name of the volume, which I would like to look at the seed density or seed volume. Now for the third parameter, you can set the address or index of the voxel. Now the current volume wrangle index is looking at ix, I at ix, I at iy, and at ic. So this is the current voxels index. So if you want to get the neighboring value in x direction, then what you need to do is to add 1 to the ix or subtract 1 with the ix. So either one works. So let's see by using add by 1 and see the neighboring check the neighbor value. Okay, and as an output, you'll be able to get the neighboring seed value. Okay, now what I want to do is, and the current seed value can be retrieved by accessing to f at seed. Okay, so next you need to create a condition if this f seed is not equal to the neighboring seed. If it's not equal, then that's where you want to fill in the density, and that's where you want to update this density value to something like 1.0. Okay, and as a result, you should be able to see something is happening here. So maybe the volume resolution is not high enough. So I'm gonna set the volume resolutions to 100. I'm gonna copy this one and paste it to the density so it shares the same density or resolutions. Now, right now the C value is a bit too noisy. We cannot see what's happening here, so I'm going to create a delete node to delete the seed partition or seed volume at this point, and select the seed. Okay, now I can only see the density volume now. Now you can see that there is some partition-like surface or volume is being filled with density equal to 1 like this. And this is actually the partition that we want to visualize as a surface. And we have just done the condition for the x direction, but by doing for all the y and z direction, as well as the negative direction, negative neighbors, you'll be able to create a completed partition conditions to fill in the density with without any gaps, without any small spaces. Okay, so to do that, to do it in one call or to do it efficiently, we're going to use a for loop for the positive and negative for the x value first. So let's do that. We're going to create a single for loop starting from -1 to +1 and added by 2, so we only check either -1 or +1. Okay, now I am going to have it right this, and then let's change this value to +I, which makes starts from -1 and also use a +1 as well in next loop. So you have two loops with this one to use I for -1 and +1. Okay, as a result, you have more thickened x directional partition. Okay, now I want to do the same for the y and z. So to do that, I'm going to create a two nested loop for the y and z, having the same loop set. So I'm going to change the variable to n for the y, and let's have it z for t. Let's also close the loop 2 times like this. Now I'm going to add n to the y and t to the z. Now I'm also need a conditions for this one, but I think it should work. Maybe not. Okay, I think I missed this comparison operator here. Now you see this partition here. Now there is also a partition on the edges right here as well, so we don't want that. So let's remove that by adding some condition here, saying if the ix is larger than 0 and ix is less than resolution x -1 for the x direction, which will delete the wall and the x direction. Do the same for the y and z. So I'm going to copy this one, copy right here, and paste it and change this to y, and do this again for the z value. So z Z, Z. Okay, now it deletes the top and side faces. Now, what I could try now is to use a volume blur to make it a bit more smoother at this point. Maybe that's too much. Okay, like this. 0.03 something. And then I am finally going to convert this into surface by using something like convert. Okay, and change this value to create a wall. And you can see that the wall has been created using a volume noise. And let's try to change the size of the volume by changing the scale value right here. So if you make this bigger, you have more cells, volume Voronoi cells, and you can see that the wall has been created. The border has been visualized as a surface like this. Okay. And if you make this jitter like 0 at some point, you have more artificial, more geometrical parts. If you keep everything to 0, you have more square like cell divisions like this. If you just set y value to 1, I'll create something like this. Looks like a honeybee, which looks interesting as well. Yep. So that's what I want to show you in the last, how you can create a border by using a Voronoi Noise information. You can do the similar things with the Worley Noise, maybe together with the Manhattan distance or Chebyshev distance might give you a more interesting results. So I suggest you try it out by yourself. You should, at this point you should be able to do it by yourself. Okay, so that's pretty much it. Now that was a lot to cover, but that was the basics of noise, how you can use each of the noise functions in Houdini, and what you can retrieve with it, what's the characteristic of each noise functions with some exercises. I hope you got the glimpse of what you can do with those noise functions. It's pretty powerful functions. You can use it for many purposes. I also tend to use it every time I do the algorithmic design for many purposes. It's pretty essential tool for the design. Now this is it for today, and now the next topic that I would like to talk about is the combination between the VEX and the solver. The basic of the combination between the VEX and the solver is what I want to talk about in next topic, which is also a must when you are doing a animation based designs or motion graphics or algorithmic design and stuff. I think there are tons of things to cover for the solver, so I might need to split it into several sections in different days, but I'm going to start with the really basics. Okay, now thank you for watching, and if you like the video, if you like the series, please press the like button, and it will be great if you could subscribe so that you can check the newest video. And I also started a Patreon page myself, and you can go to the page from the video description page from the YouTube, and if you are kind enough to support me, I would really appreciate it. Okay, thank you very much, and see you next time.